Let's skip 7.1 and go straight to 7.2. Why am I saying we must skip 7.1? I don't want to break a lot of hearts. A lot of people got 7.1 wrong. There's a word that they miss at the end of the definition. So I don't want all that smoke. Let's just skip 7.1 and go to 7.2. So write down the formula of the conjugate acid of the carbonate ion 7.2 CO3 to the 2 minus. Well, we can answer this question without any context, but let's just take a look at the question statement. Hydrated potassium carbonate K2CO3 H2O is a weak base. A solution is prepared by dissolving some of this solid in water. So what is the conjugate acid, right? It is the ion that is formed when these bases accept a hydrogen, right? So the answer to 7.2 is HCO3 to the minus, right? No longer to the 2 minus, but just to the minus, because we have accepted a hydrogen. So, well, we have accepted a hydrogen plus we have accepted a proton. So it must be to the minus and not to the 2 minus. Hope you didn't make that mistake. 7.2. Okay, let's hear the stories. In 7.3, a hydrochloric acid solution HCl of concentration 0.1 mole per decimeter cube is titrated with the prepared potassium carbonate solution of unknown concentration. The balanced equation for the reaction is K2CO3 plus 2HCl to give us, 2KCl plus CO2 plus H2O. And then the equations 7.3.1 determine the value of P. Okay, so let's take a look at what happens. We have two runs. In run 1 and 2, the volume of HCl used is the same, right? 25 centimeter cube. Okay, and then in run 1, where we find a P, we are given the initial burette reading of K2CO3. It is 6.5. And then the final reading of the burette is P, which is unknown, right? And the volume of K2CO3 that is used is 20.05. And we are looking for the value of P. Well, this is how a burette looks like, right? Let me just put a sketch real quick, and so the readings on a burette, they start low, and as you go down they get high. So here you will find something like 5, 10, 20, 25. This is how the readings on a burette look like. So the final reading will always be greater than the initial reading in a burette, right? Because the numbers, they increase as you go down. So the volume of K2CO3 used is 20.05 in run 1, right? And the initial reading on the burette was 6.5. So the initial reading was somewhere here, 6.5. And we know that 20.05 is used. So what should be the final reading if 20.05 is used? Well, we just say that P is equals to 6.5 plus 20.05. So let me just put that in my calculator. 6.5 plus 20.05. I'm getting 26.55. So the final reading, so the initial was somewhere here, 6.5, and then the final reading was somewhere here, 26.55. This is the initial reading, and then this is the final reading on the burette, because the numbers go up as you go down. So this is the answer to question 7.3.1. that is the value of P. Okay, and then 7.3.2, we're looking for the value of Q. So Q, which we have here, is the initial reading, right? So how are we going to find the Q? We're just going to see the volume, the final reading, which is 48.3 minus the volume that is used, 20.15. So 48.3 minus 20.15, this is 28.15. Yes, so Q is equals to 28.15. That is the value of Q. That is the value of P. Okay, and then 7.4, methyl orange is used as the indicator. explain why methyl orange is most suitable indicator for this titration by referring to the pH at the equivalence point. Okay, so we need to break down this reaction that we have, right? We have K2CO3 and HCl. So K2CO3, if we are to use methyl orange, should be a weak base, right? So we have a weak base plus a strong acid. The equivalence point when we have a weak acid and a weak base and a strong acid, the pH should be less than 7 at the equivalence point, right? Around about 3 to 5. This should be the range of the pH at the equivalence point. And we know that methyl orange changes color along that range. That's why we use it to determine the equivalence point when we have such a reaction between a weak base and a strong acid. Okay, and then 7.5 for 5 marks, we are supposed to calculate the concentration of K2CO3. So I wonder what information we have, but let's take a look. So we have K2CO3 plus HCl. So this is what we are dealing with. We're supposed to use these two to somehow find the concentration of K2CO3. Okay, so let's take a look. So obviously we want the concentration of K2CO3. So already that tells me that I need to somehow use information that I have with regards to HCl and use that information to find something with regards to K2CO3, because chemistry essentially, right, it's about using what you have to calculate what you don't. So let's see how we can do that. Let's see the information that we have. We have the concentration of HCl. So the concentration of HCl is said to be, so C is equals to 0.1 mole per decimeter cube. And then what about the volume of HCl? So we can use, oh, well, it is given to us as 25 centimeter cube. So 25 centimeter cube. So already looking at these variables, I can find the number of moles of acid, right, HCl. With the number of moles of acid, use balancing coefficients, find the number of moles of base. With the number of moles of base, I just need the volume of the base to therefore find the concentration of K2CO3. Okay, so which volume of K2CO3 am I going to use? We have 20.05 in run 1, and then in run 2 we have 20.15. So which one do we pick between these two? Which one are we going to use? A bit tricky really. But I think we have 3 options here. I think we can use run 1, that would be fine. And then we can use run 2, and that should also be fine. Yeah, because the volume of HCl used is the same. So if the volume of HCl used was different, then we were going to use it as a coordinate. Take the volume of HCl and its corresponding volume of K2CO3. But here we have 2 different volumes. Or better, we can add the 2 volumes and divide by 2 and use the average volume. All right. I think that will also be fine. I think we have that freedom of choice. Okay, so let's go. We're gonna add the 2 volumes and we're gonna use the average. So the number of moles of HCl CV. So we have 0.1, 25 over 1000. So let me put that in my calculator. So 0.1 multiplied by 25 over 1000. I'm getting 0.0025 moles. This is the number of moles of acid. Let's check the balancing coefficients. We have 1:2, right? So we can say that the number of moles of acid is to the number of moles of base. We have 2:1. So that of acid is 0.0025. We can just divide that by 2 to find that of base. So we have 0.00125. This is the number of moles of base. So we have the number of moles of base. We are looking for the concentration. Volume, we said that we're going to add the 2 and divide by 2. So 20.05 plus 20.15 divided by 2, 20.1. So I'm going to use a volume of 20.1. I'm going to find the average of the two. So the concentration, the number of moles over volume, number of moles is 0.00125, and the volume is 20.1 divided by 1000. So I can just multiply with 10 to the minus 3. So 0.00125 divided by 20.1 times 10 to the minus 3. I'm getting 0.062 moles per decimeter cube. This is the the concentration of K2CO3 that I end up with. Okay, and then now let's go to 7.6. Right. So the value of X. So we're going to do 7.6. After 7.6, after question 7, really, we should do question 8, 9, and then we go to question 1 and do the multiple choice. But it's going to depend on the value of X that I get. When I calculate the X, I want the whole number, right? If I don't get a whole number, we're done. Yeah, so if you want to watch me do question 8, 9, and 1, hope that we get a whole number, because if we don't get a whole number for the value of X, I'm not going to think that the question is wrong. I'm going to think that I am wrong, and we're going to call it quits. So let's see. The above K2CO3 solution is used. The above K2CO3 solution used in the titration was prepared by completely dissolving. So we have a mass there of the hydrated potassium carbonate, 6.525 grams, in 600 centimeter cube of water. And then the question says calculate the value of X in the formula. So, okay, this is what I'm thinking. So the volume that this mass was dissolved in is 600 centimeter cube, right? But the volume that was used, I don't even know how to name these things. So this is the volume that was used to prepare. And then the volume used, if you look at run 1 and, oh, well, am I looking at the right thing? No, I'm not supposed to look at run 1. Yes, I am supposed to look at run 1, but not ACL. I'm supposed to look at K2CO3. Yeah, if you look at the volume of K2CO3 used in run 1, it is 20.05. And then in run 2, it is 20.15. So let's carry on using the average, right? The volume used is 20.1 centimeter cube. And what number of moles were present in this 20.1 centimeter cube? Let's find out. We had 0.00125 number of moles present in a volume of 20.1 centimeter cube. So the number of moles here is 0.00125 moles. Yeah, so these are the number of moles present in 20.1 centimeter cube. But we know that this mass was dissolved in 600 centimeter cube. So what is the number of moles present in 600 centimeter cube, right? That's the question I'm asking myself. How am I going to find that? I'm going to say number of moles in 600 centimeter cube should be equals to 0.00125, the number of moles in 20.1 centimeter cube, right? Multiplied by 600 divided by 20.1, because these are the number of moles in 20.1 centimeter cube. But we know that the mass was originally dissolved in 600 centimeter cube. So how many number of moles are present in the 600 centimeter cube? That's what we are trying to find here. So this is going to be equals to, so let me just put that in my calculator. 0.00125 multiplied by 600 divided by 20.1. I'm getting 0.033 3 7 3 1. Let me just look at my substitution once more and see that I've not done anything wrong. So this is 0.00125 is fine, and then 600 divided by 20.1, 0.03731 moles. Okay, so these are the number of moles when we dissolve 6.525 grams of the hydrated potassium carbonate in 600 centimeter cube of water. Okay, so we have the number of moles, we have the mass, we can find the molar mass. This is how I want to find X. So I'm going to say that number of moles is equals to mass divided by molar mass. The number of moles that we find in 600 centimeter cube, it's 0.03731. The mass used is 6.525. So here, in place of molar mass, it's where the X is going to come in play, and we will try and find it. So let me take my periodic table. K, where is K? Potassium 39, right? So okay, I'm just going to put this in my calculator and write one value. So 39 multiplied by 2, right? I'm putting K2CO3, and then I'm gonna say plus, and then put X multiplied by the molar mass of H2O. Okay, carbon K2CO3, carbon is 12, oxygen is 16, we multiply by 3, we get 138. So I have 138 plus X multiplied by the molar mass of H2O. So H2O 1 multiplied by 2 plus 16, 18. So 18X. Let's just write this as 18X. 18X. Okay, so now the problem becomes mathematical. 0.03731 multiplied by 138. So I'm getting 5.14878 plus 0.03731 multiplied by 18x plus 0.67158x is equals to 6.525. So obviously I'm gonna take this to the left hand side. So 6.525 minus, is this 5? Is this 5? Is this 5? Okay, let me multiply 138 with 0.03731 again. 5.1485. So this is 5. Yeah, I think I don't want to get to the final answer. I'm taking as long as I can because I don't want to get to the final answer. Yeah, this question is really freaking me out. So 6.525 minus 5.14878. So 0.67158x is equals to, I press answer, I get 1.37622. So x is equals to 1.37622 divided by 0.67158. I'm having a lot of fun, to be honest. So I just need to put this in my calculator. I'm not sure I want to. Because if this answer is not a whole number, I'm not carrying on. Okay, moment of truth. I get 2.005. I get 2.05. So can we say that x is equals to 2? Can you say that? Yeah, maybe because I'm not rounding off here, that's why I'm not getting exactly 2. But there we go. X is equals to 2. When I do this, when I use this approach, this is the answer that I'm getting. Yeah. So let me know in the comments, which approach did you use and which answer did you get? And when you're taking a look at my approach, can you tell me where I am lying? Right? Yeah, because I can sort of justify what I'm writing, but maybe there's an assumption that I'm making which is not necessarily true. So let me know in the comments, where am I lying here? Where am I lying? Do you get the same answer? If not, what answer do you get? Here we go.